In the previous video we looked at nuclear fusion. In this video we're going to look at a different type of nuclear reaction known as nuclear fission. Whereas fusion was the joining of two nuclei, fission is the splitting of a larger nucleus into smaller nuclei. What we also usually typically see is that we end up with not just those two smaller nuclei being produced, but usually some neutrons being released as well. So that's basically just a result of the fracturing of a large nucleus into smaller parts. There's also some other bits and pieces that are released, and that doesn't usually just happen naturally. It's usually caused by bombarding the nucleus with a neutron. So it's a process that requires some input to begin with, and it's not one that usually occurs naturally. There are some examples of it occurring naturally in the past, but usually it's a process that requires sort of it to be initiated by a neutron. So an example that we'll look at here, so we'll have a neutron here that's travelling up towards another nucleus, so the symbol for a neutron is 10N, and imagine that we've got another nucleus up here somewhere, not to scale necessarily, just going to draw it as a representation so we've got a bit of a sense of what's going on with this process. So here's a nucleus with a whole bunch of protons and neutrons in it, and this particular nucleus, one that's fairly commonly used for nuclear fission processes, is uranium-235. So that's 235-92U, and once that neutron bombards the uranium-235, it will split into two smaller nuclei, so represented by what happens over on the right here. And so again we'd have our smaller nuclei, again not to scale but just to provide a bit of a diagrammatic representation. So there's a bunch of protons and neutrons here, and then another smaller nucleus down here as well. For one particular example, so this isn't always going to be the outcome, but in this particular example we're going to say that the products are 9438, which is a strontium isotope, and 13954, which is xenon. Now what we also see in this particular case is a bunch of 3 neutrons that are also ejected, well not ejected so much as produced from this reaction. So 3 lots of neutrons there. Now other combinations are also possible here as well, as I said. This is just one possible result, and we'll have a look in a bit more detail in class at what some of the other possible combinations are and what some of the probabilities are in that regard. So other possible combinations of the product nuclei. Again, if we look at the equation for this one, would be 10N plus 235-92U goes to give us those 2 isotopes of strontium 94 plus the xenon 139 and those additional 3 nuclei. Now in some cases you might be told what these products are, and you might need to then figure out how many neutrons are also produced. It's just a matter again of balancing the mass numbers and the atomic numbers. The other thing that's interesting to note here too, we had one neutron that was bombarding this uranium-235, and in the process we've released 3 more neutrons as well. So those 3 neutrons in a large sample of uranium, those 3 neutrons could then go on to bombard even more uranium-235 nuclei, and so we'd get what's known as a chain reaction by all of those neutrons causing more and more uranium-235 to undergo a fission reaction, releasing quite a lot of energy. If that's a controlled process, that's what's used in nuclear power plants. In an uncontrolled process, we've got another type of nuclear bomb there. Interestingly, for the hydrogen bomb I mentioned in the previous video, you actually need a fission reaction to start it in order for the fusion to then occur. Now, moving back to similar points that we made in the last video, again we have that the product nuclei have a higher binding energy per nucleus. Per nucleon. Keep saying the wrong word there, I apologise for that. And so that basically means that we're always going to be sort of shifting from further on the right hand end of the the binding energy per nucleon graph, and sort of shifting to the left as we get to smaller and more a higher binding energy per nucleon. It also means that we won't usually see anything smaller than iron undergoing fission, because again the binding energy per nucleon would be decreasing if we broke something that size into smaller parts. Again, as we saw with fusion, the total mass of the products is less than the mass of the reactants. And again, the difference is converted to kinetic energy of the products. Sorry, difference. So converted to kinetic energy of the products. Again, if we look at the example of the reaction that we jotted down above, keeping in mind here that we actually need to consider the mass of the neutron, both in the reactants and the products, which has a mass of 1.008665. The mass of the uranium-235, I'm just going to shorten this notation and go this way. So the uranium-235 has a mass of 235.043929 atomic mass units. Now I'm jotting these down so that if you want to go through and check them yourselves, just to make sure that you can see where the values that we get come from for the change in the mass and the amount of energy, would be a good idea just to run it through your calculator quickly so that you know that you understand the calculation. And finally, the mass of the xenon 139 is 138.918793. So keep in mind that the reactants are these two, but then with the products we've got both these two and 3 neutrons as well. So if you are going to do that calculation, don't forget the mass of the neutrons. Now the difference in mass in this situation comes out to be 0.192445 atomic mass units, and again using the conversion that 1 atomic mass unit is equivalent to 931.5 mega electron volts, we end up with 179.166 mega electron volts released. If you compare this amount of energy to the amount that we calculated for the fusion reaction, you'll notice that it's much greater for fission than it is for fusion. And that is true that a fission reaction typically will release more energy than a fusion reaction when we consider just a single event, so one fission and one fusion reaction. However, if we consider the amount of energy released per kilogram of the reactant, fusion usually releases much more. That's largely because the particles that are being fused together in a fusion reaction are so much smaller than the isotope that's undergoing a fission reaction, and so as a result we typically see much more energy per kilogram of reactant for fusion. We'll have a look at that in class in a bit more detail and look at a couple of scenarios and do a direct comparison there to see the difference between the amount per kilogram.